In this video, I'm going to solve the ALEKS problem called Solving Applied Density Problems. This is a really tricky problem, and there are a lot of variations on this problem, so I'm not going to be able to show you how to solve every single one of them, but I will walk you through the process of how this particular problem gets solved, and hopefully it's helpful for the other versions of this problem as well. So in this problem, the situation is that these people want to make a hollow sphere made out of gold so that it would replicate the density or the mass of a solid sphere that was made out of iron. And the problem is giving us the density of the gold, and it's also giving us the density of iron, and it is giving us the necessary dimensions of the sphere. So the way that I would go about solving this particular problem is that I would begin by calculating the mass of the sphere. 8 centimeters is its diameter. The mass of an 8 centimeter diameter sphere if it was made of solid gold. So I'm going to figure that out first. And then I'm going to calculate the mass of that same sphere, 8 centimeters diameter, if it was made out of solid iron. And this is going to give me an idea of how much the solid gold sphere, by how much it is too heavy. So I'm going to calculate the extra mass, or how too heavy the gold sphere is. So I'm going to calculate the extra mass of the gold sphere, and that's going to give me some information about how much mass of the gold sphere, how much mass of the gold needs to be removed to make it weigh the same as a sphere made out of iron. And let's just start with that, because that's quite a bit. That's not going to get us all the way to the end, but let's just start with that. To calculate the mass, or to calculate the masses of these spheres, we're going to have to first calculate the volume of the sphere. I'm going to do that up in the corner here. The volume of a sphere is calculated by the equation 4/3 pi r cubed. This particular sphere has a diameter of 8 centimeters. Let me just double check and make sure it's a diameter. Yeah, it's a diameter of 8 centimeters, so that means its radius is 4 centimeters. And I'm going to use that to calculate the volume of this 8 centimeter sphere if it was solid. 4/3 pi, the radius is 4 centimeters, and that's going to get cubed. Let's do the math on that. 4/3 times pi times 4 cubed gives us 268 cubic centimeters. And a really important relationship in this problem is that 1 cubic centimeter is equal to 1 milliliter. Oh, actually, as I'm saying that, I'm realizing that the densities were actually given to us in cubic centimeters, so we don't even need to worry about that at all. Let's just pretend I didn't say that. Okay, so here's the volume of the 8 centimeter diameter sphere, or 4 centimeter radius sphere. With this volume, let's now calculate the mass of the sphere if it was made of solid gold. The relationship between the volume and the mass of any object is that object's density. So we have been given the density of gold, which is 19.8 grams per cubic centimeter. We determined that this sphere had a volume of 268 cubic centimeters. If it is not hollow, 268 cubic centimeters. Take a look at how those cubic centimeter units are going to cancel out, and this is going to leave us with just mass in terms of grams. We're going to take 19.8 and multiply it by 268, and that gives us a mass of 5,308 grams. So that's how much the sphere would weigh if it was solid gold. 5,308 grams. Now what we're going to do is calculate the mass of the sphere if it was made of solid iron. To do that, we're going to use the density of iron. It was provided to us, 5.15 grams per cubic, 5.15 grams per cubic centimeter. We're going to multiply it by the volume of the sphere. Remember, it's the same size sphere in both situations. 5.15 times 268 is 1,380 grams. So if we had a sphere that was made out of solid iron, it would be having a mass of 1,380 grams. So now that we've got that much, let's take a minute and think about what we've calculated. In this situation, these people are trying to make spheres of gold, hollow spheres of gold, that would have the same mass as a solid sphere of iron. So we have determined that a solid sphere of iron with this radius would have a mass of 1,380 grams. If this sphere was made out of solid gold, which isn't even the plan, right? But if it was made out of solid gold, it would have a mass of 5,380 grams. So comparing these two numbers is going to give us an idea of how much we need to hollow out from this gold sphere in order to give it the same mass as that of a sphere of iron. So what we're going to do next is calculate that extra mass. How much mass of the silver needs to be removed so that this sphere will weigh the same as a same-sized sphere of iron. That's just going to be the difference between those two masses. So the mass of the hypothetical solid gold sphere, 5,380, subtract the mass if it was iron, 1,380. I said 80, but I should have said 08. 5,308 minus 1,380 is telling us that we have 3,928 grams of extra mass of the gold, and this is the mass that needs to be removed. So in order to make this sphere weigh the same, in order to make a gold sphere weigh the same as an iron sphere, we've got to chip 3,928 grams out of the center of this sphere. How are we going to figure out how much, in terms of volume, how are we going to figure out how much to chip out? That's going to be our next step. We're going to calculate the volume, the spherical volume to be removed from the gold sphere. We know that we need to take 3,928 grams out of it. What volume corresponds to 3,928 grams? Let's do that calculation over here. See if I can fit it over here. 3,928 grams, which we need to be removed. The relationship between mass and volume, again, is our density. Our density for the gold is, write it up here, 19.3 grams per centimeters cubed. Right now, we have our mass of gold in units of grams, and we're trying to convert that mass into a volume. So we need to multiply by a conversion factor that has grams on the bottom so that that gram unit will cancel, and cubic centimeters on top. Now, the density for gold given to us in this format is not set up properly for us to use in this equation because the grams are on the wrong side of the conversion factor. We need grams on the bottom, and right now they're on top. But remember, with all conversion factors, we can just flip them upside down as needed to make them work for us. So I'm going to turn this conversion factor upside down, 1 cubic centimeter over 19.3 grams. That's going to set it up in the way that I need it to be set up to be able to use it for this conversion. Okay, so I'm going to give myself a little bit more room here, and I'm going to multiply by my conversion factor, which is 1 cubic centimeter over 19.3 grams. My gram units are going to cancel, And this is going to give me, oh, not times, answer divided by 19.3. This is giving me 203.5 cubic centimeters. That is the volume that I need to remove from the inside of the sphere. So I'm making good progress at this point. So I have figured out that I'm going to chip this much away. The problem is asking me, let's go back and see what it's actually asking. What is the required thickness of the wall? So it's asking how big is this, how big should this thickness be? I know that the whole entire thing is 8 centimeters across, or 4 centimeters in terms of the diameter. It wants me to know, it wants me to calculate what that number is. So what I need to do next is calculate the radius of this hollow sphere on the inside of this big huge lump of gold. The radius, to get the radius, I'm going to go back to this volume equation. I just calculated the volume that I need to remove, so I have the ability to calculate the radius of this hollow spot. Now, I'm starting to run out of room here, so I think what I'm going to do is take, I think I'm just going to erase this stuff over here. I have to get rid of it. So calculate the volume to be removed. Once we know the volume, we are going to calculate the radius of the volume that we're removing. I'm going to use the equation for the volume of a sphere. Volume equals 4/3 pi r cubed. I know my volume. I got to go find it again. The volume is 203.5 centimeters cubed. 203.5 cubic centimeters. This is such a beast of a problem. That's equal to 4/3 pi times the radius cubed. So I'm going to divide both sides of this equation by 4/3 pi so that that cancels out. And we'll solve for the radius cubed. 203.5 divided by 4/3 pi gives us 48.6 as our centimeters cubed is equal to r cubed. To solve for the radius, we're just going to take the cube root of both sides of this equation, which is the same as raising it to the 1/3 power. The radius is 3.65 centimeters. And again, what I just calculated there is the radius that I need to, the radius of the portion that I need to remove. So the radius of this inner portion right here is 3.65 centimeters. The radius of the whole entire sphere is 4 centimeters. And I do not know what I just did to my calculator. So what I'm going to do last is take that radius of the whole entire sphere. From that, I'm going to subtract the radius of the hollow portion of the sphere, and that's going to give me the thickness of that shell on the outside of the sphere. The thickness of the wall to 2 significant digits is 0.35 centimeters. Like I said, this is a brutal problem, and they are not all exactly the same as this one, but hopefully watching me solve this problem will give you some inspiration for the other versions of this problem as well.